Welcome, ladies and gentlemen. I'm here to talk about the future of cell therapy manufacturing and the application of acoustics to that future. So, maybe a little science to start things off. What we do in the FloDesign system is we do our processing in a closed disposable fluid path, and we have a piezoelectric transducer on the side of the chamber which propagates a wave across the fluid. You can see then that wave is reflected by, in the case of the example on screen, a glass reflector which is facing out to the theatre. And as those waves, and that sets up a pattern of three-dimensional standing waves within the acoustic flow chamber. And as cells then enter the flow, the waves scatter off the cells as they come into the flow chamber, and that scattering action produces a pressure force on the cell to move them towards to catch them in the flow. The fluid continues to go, but the acoustics is holding the cells in the chamber, and that pressure force is pushing those cells gently together to form clusters at the nodes within the standing wave field there. If there's enough cells entering the flow and coming into the fluid chamber, the cells cluster together at those nodes, and because gravity works to the square of the radius, as the clusters increase in size, you get a squared doubling force. So if they increase 100 times in size, you'll get a 10,000 G force settling those cells to the bottom. So if we look at this little video here on the side, this is a falcon tube in front of a long piezoelectric transducer reflecting back into the page, and this is actually a 2-minute or a compression of a 10-minute settling video that showed the fully suspended cells coming down to what I would term as a slippery pellet in the bottom, which can be resuspended very readily with a couple of shakes of the tube, but it's a very rapid collection and settling of those cells into the bottom of the tube. So what does acoustics do for the processing of cells? Well, it's a non-invasive, very low shear technique. We've calculated that the cells are only suffering it's like 200 inverse seconds of shear stress in the process. So there's no centrifugation, there's no filtration, there's no bumbling across a spinning filter or anything like that. So it's very gentle on the cells. It's a closed system. It can be easily automated. You can do a continuous or batch processing. If we're using it for cell selection, we can use a non-magnetic bead, so you don't have any magnetic beads in the system. You can use an inert bead, bind it to the cell, and then manipulate the cell and bead aggregate with the acoustics. We're developing a system that is scalable through process development and flexible enough for that process development to occur, but it is really designed to be a piece of GMP-ready manufacturing equipment. And we have many applications within the cell therapy manufacturing process that we believe acoustics can be add value to. So the goal there is to solve our industry challenges, drive the cogs down, consolidate and simplify manufacturing at a high quality, and again, to move from PD to GMP with a scalable system that shows the cells the same cell journey, whether it's in a 1 ml chamber or it's in a litre chamber. So what's our strategy? We're looking to close and automate the system. We're producing modular equipment with very simple to use disposables that can be just clipped onto the front of the device. The first application that we're launching is a concentrate wash. We have a cell retention function where we can use the field as the filter on the outlet line or the recirc line for a stirred tank bioreactor or a Zuri. So the acoustic field stops the cells entering the waste line and returns them to the fluid, but the waste is drawn off gently to a waste bag. We're also working with the affinity beads, as I said earlier, to do acoustic affinity cell selection, and we have some applications on the drawing board where we believe we can bring particles, be they virus or beads, in close contact with the cells suspended in the field to become more efficient at the activation, transduction and transfection processes. And even further, I guess, to our portfolio, on the drawing board is an angled wave device which should enable us to do a label-free selection and sorting of cells, so we can, just with the acoustics and the acoustic properties of the different cell types, be able to split up a mixed population of cells into the cells of interest. So if we look at the cell and gene therapy unit operations, whether you're autologous or allogeneic, you have to do a selection step. You do cell modification or engineering, you do cell culture, cell harvest, formulation, and fill and finish. And if we even look to viral vector manufacturing, you have some activity there. Now, if we map the acoustic operations to each of those steps in the manufacturing process, we believe that with acoustics, we can do the selection either with an affinity acoustic bead or with our label-free technology. We can then do the concentrate wash, which happens after the selection process and before the modification process. Then you can actually activate your cells of interest with a particle, or you can run transduction after that and transfection by bringing the virus and the particles close together in the acoustic field and then transferring them through another concentrate wash step to the cell culture stage. In cell culture, we've got two applications that are of interest there. The cell retention that I talked about earlier, where the waste stream of a bioreactor is drawn through normally a tangential flow filter or something of that ilk. In our case, there's the acoustic field with the edge effect, which is pushing the cells down and keeping them in the recirculation loop to go back to the bioreactor, and the waste fluid is drawn off through that acoustic field. Alternatively, we're experimenting at an autologous level with suspending the whole patient sample of cells in the acoustic field and gently perfusing the media through that field. So we actually are exploring the use of the acoustics as a cell culture bioreactor at an autologous scale. Then we go, after an expansion harvest, you again need to do the concentrate wash, and if you're perhaps doing an allogeneic T-cell process, you might again do an affinity cell selection to get rid of the cells that you don't want out of that allogeneic population. So you would run the harvested cells through a column. The activated beads in there are binding to the cells that you don't want to go in the patient, and all the other cells go through the field at the top and are in the harvest bag. And then again, you would need to concentrate wash that before going to your final formulation step. If we think about viral vector manufacturing, the cell retention function as part of the bioreactor, you can draw off your harvest stream through the cell, through the acoustic field, return the cells into the bioreactor. And if we think about the logical extension of the angled wave, which is differentiating particles on size, compressibility, and density, you could potentially even separate the empty versus full capsids and do a fractionation there, so you get a better yield of more potent virus. And then you can imagine how you would use that to do the viral concentration rather than an ultrafiltration step. So if I look at our pipeline of applications that we're working on at the moment, we have a 1 litre concentrate wash, both at a low and high density, which is generating customer data at the moment. We're going to be launching that product in Q4 this year or Q1 next year. We have the cell retention, which is on the same time frame. We can scale that 1 litre process to 5 litres. So that's probably a little bit behind the other ones, but coming out in Q1 next year at the expanded scale for the concentrate wash. The affinity selection, that's going to be launched around the middle of next year. And I'd like to draw your attention to the next one, the FDS acoustic module. We're going to be making the technology available for incorporation into other pieces, manufacturing systems, so they can use acoustics to do their concentrate wash or whichever process step they want to, and marry it to their existing other processes that they're implementing in their equipment. And that will give us the ability to spread acoustics across the market into more products than just the ones that FDS are offering. After that acoustic module, which should be available towards the end of next year, we have the acoustic affinity positive selection, which is slated towards the end of next year. And then, as I said, those other applications are waiting for us to have resource, funding, and a partner to progress them up our pipeline. So there's a couple of images on this slide about the prototypes that are in existence at the moment. Up here we have the concentrate wash device in the early form, where the cadence system, which Paul have licensed from FDS, it's used for the production of MABs. They do clarification and concentration of their MAB product with acoustics at a development system of 10 to 50 litres, but in production up to 1,000 litre bioreactor. So what this gives us is the strong confidence that acoustics can be scaled to any level required by cell and gene therapy. On the right here is the cell retention for cell culture, as we were talking about before, and the acoustic affinity and the activation transduction, which all would occur in these columns of these devices. So we feel that acoustics delivers the potential cost saving. The way I feel about this is each individual unit process costs a certain amount to run in your manufacturing process, but as we develop more applications for acoustic within the process, it gives us the ability to meld process steps together to have one consumable, perhaps doing 2 or 3 unit processes at once, and thereby drive the cost of the production process down. So we believe we can deliver significant cost of goods savings. We have a technology that enables us to close, simplify, automate, and be integrated into both process development and manufacturing. And the unit, the unique capabilities of acoustics with the low shear gives us the ability to do all of these manipulations in a low-touch, shear-free environment. So here's a quick look at our hardware and launch timetable. We're sitting at the moment here. We have